Okay. We are live. Yay. All right. Habit of Code. It's going to be day 6 in about 20 minutes, but before then, I need to finish day 5 because I didn't yesterday because it got too late and I had an issue with my code. So, as a refresher, we have a bunch of lists of numbers and we have some rules for how the numbers go together. So this is saying that if we have 53 in our list of numbers, then we have to have seen 47 before we see 53. So this would be valid because 47 comes before 53. And in the second part of the puzzle, we have to, so we have in the first part we have some that are properly ordered and some that are not properly ordered. In the second part, we have to take the ones that aren't properly ordered and have to make them properly ordered and then do the same thing where we get the sum of the middle elements, like we did in the first one. So my approach, which I'm standing by, is to have all of the bad sequences and just randomly scramble them until they become valid. Because like I said yesterday, I have more brain cells than I have. Sorry, I have more compute than I have brain cells. So there's that. All right. Let's see if we can do this a little bit better than I was doing yesterday. I'm gonna switch these real quick just so I can see. Cool. So yesterday my approach was the same, but I think I coded it badly. So I'm going to do the same thing, except a little bit different. I'm going to move this validation into a function itself, so that I'm not having to deal with like duplicated variables or anything. Is sequence good? And then we'll just have this be inside the function. I copy this from here, so that should actually do what we want, and then we can return sequence good. And then rules dict, we'll have to pass in rules dict, and this is sequence. Let's see. Sequence.split on comma. Yeah, sorry, I'm just refamiliarizing myself with all this code that I slammed out yesterday when I was half asleep. Sequence good. So I think this will do what we want. If we can just substitute this in for part 1, I'll be convinced that we can use this. And I've also only got 15 minutes until the next one starts, so I've got to finish this by then. So we've got to pass sequence, and we've got to pass a rules dict. S, and then rules dict. So let's try part 1 again with that and see if that works. If it does, I'll be convinced that. Okay. S. Unsupported operand types for int and string. What's our issue here? I'm baffled by this. Plus equals total 0. Let's print out an S. Let's see what we're actually getting. 53 and 13. Oh, should this be... What? Oh, this should be... What? What have I done here? Is sequence good? Nums is... This should be... Why did I write this way? Okay, let's print good sequences and see what we got. Oh, okay. So this should be right. This should be. So is sequence good? Should take. We should do this first. For this would be nums. We'll call this nums. Oh man, for s.split. Still? Oh, because we're still pending. There we go. Okay, cool. That's, I think, what we want. 143 is the example. Cool. Okay. So then for part 2, we can do for s in sequences. Yeah, so we still want to get that same thing. I'm just going to cut all this out. If not, is sequence good? We will bad sequences dot append nums. Bad sequences is this. We've got our rules, we've got our nums, and then let's print our bad sequences at the end. Why do we have good sequences here still? It seems like the wrong thing. Okay. Try part 2. Okay, so these are the bad sequences, right? 61, 53, 13, 29, 47. Great. Cool. So we're gonna okay, so we're gonna do this exact same thing. Actually, we don't even need a second step, I think. I think we can just, well, it's not good, we'll do nums.shuffle, and then when it's good, we'll do bad sequences.append nums. So list has, oh, it's a random.shuffle nums. Well, it's not good. Sequences don't append. Oh, okay. So we do have to. This is stupid. This is dumb. I should do the actual right thing. I've spent more time doing the wrong thing than I probably would take to actually just do the right thing. We'll just do the same thing again for S in bad sequences. We don't have to do the nums anymore. And then we can do, so that's why I had good sequences. It's this, and then we'll do this. Good sequences. This should be S, and then we'll do random.shuffle S. And then we'll print good sequences at the end, and hopefully we'll get what we want. Oh boy. Something's going wrong here. So why are we just spinning? We're not even, well, not is sequence good, nums. Oh, because we're just depending, we're not ever, right, this isn't what we want to do. This is not, that should be an if, not a while. Okay, so 97, 13, 97, 75, 47, 61, 53, that's right, 61, 29, 13, 97, 75, 47, 29, cool, that's what we want. So our approach works, and then at the end, we can just do the same thing that we did in part 1, and I've got 8 minutes. So hopefully this takes less than 8 minutes to run. Colon 23. Excellent. All right. So our lazy, terrible, non-optimized random approach works. That's day 4. That's not actually. We want to do it all. We want our day 5 input. Cool. So this is random sort. Oh boy, this is gonna be a while. As soon as it doesn't complete immediately, you know it's gonna take a long time. So I guess we'll just sit here and wait for this to spin. And hopefully at some point we'll actually get the answer. One thing that would be fun to do, just to see if this is actually working, is every time we append a proper answer, we'll do got an answer. Then we'll do length of good sequences, just for sanity, to make sure that, oh my goodness, that something's actually happening and that we're not just sitting here spinning. Oh, so I gotta do day 5. Uh-oh. So either we've got a global interpreter lock going or something. Yeah, I should print. Well, I guess my YouTube chat overlay is not working. I should print when it finishes one of the lists successfully, so I know what it's up to. Yeah, that's a good call there. All right, so that took what, 30 seconds for the first one. How many do we have here? Oh no. And that's not even the longest one. Yikes. All right, well. That's exciting. What have we got? 1,000 of these? 1379 to... it's not 1,000. 1379. Okay, so we've got 200. Is that all? Okay, so yeah, this is gonna be a while. Potentially over an hour. So I don't need to run this twice. So I'm gonna delete that terminal. Yikes, man. This is so the wrong thing. Anyway, we've got 5 minutes till the next one, so I think we can just sit and let this spin while we solve it. The right thing to do, probably, is to, like, smartly sort the list, because, obviously. One thing we could do for that is we can pass, like, a custom function to sort it in Python. This is a function, right? What is sorted? What is sorted docs? This dot sort. I think we can. Yeah. Use to extract a comparison key from each element. Okay, yeah, so this can be a function. So probably what we want to do is pass a function to this sort function as our key that tells it the priority of 2 keys. So like if 57 needs to come before 43, then we can pass a function that knows about our rules here and says if we have 57 and 43, that we can compare the two. I'm wondering if that would actually work. I think it probably would. Yeah, okay, this might actually end up being computationally intractable, which I wouldn't be too shocked at. The other thought I have that I haven't put too much thought into is maybe we can just like find a cycle of numbers that are dependent. If that makes sense, then we can just follow it all the way through until we end up with a list that is correct. Oh, this is the really cursed a cappella song. I wish there were more than like 6 Christmas songs in this playlist. Anyway, this is gonna take forever. We're gonna have to be smarter about this, I think, which is really sad because I didn't want to. Really cool of my chat overlay to just not work. Anyway, whatever. 5 minutes or 3 minutes now, actually, to the next one. So I think we're gonna leave this for now, and we'll come back after day 6 and see if we can improve. I think it would be hard not to improve, so I'm really hoping we can. I'm just looking at I guess I'll just do some more research about this. Python sort lambda key. Yeah, okay, cool. Yeah, so I think that approach will work. It's not really that complicated. I guess I can try and start. Def compare. As long as we can, yeah, I think we can just have the rules be kind of a top level variable thing here. And yeah. A, B. And then, yeah, we can just compare based on whatever our rules are. Where's the actual validation of A not rules dict? No. The sequence good. That's what the logic's actually going to be. So I think it's just going to be something like this. I'm going to go back to the advent of code right now, though, because we're about to have the next day unlocked. So it's going to be something like that. If A and rules dict, this is going to be A. All right. And I've somehow got to pass nums there too. Anyway. Oh boy. Dropping day 5 for now. We'll pick it back up in a bit. We still only found the first one. That's super rough. All right, 5 seconds. Cool. Got a device. In the year 1518. I wonder if this is a 2018. Just have to be careful of time paradoxes. Single guards patrolling the lab. Start by making a map. The map shows the current position of the guard with this. They're just currently facing up. And guards of 1518 follow very strict patrol, which involves repeatedly taking these following steps. If there's something directly in front of you, turn right 90 degrees, otherwise take a step forward. Okay. Okay. There's now an obstacle in front of the guard. She turns right for to straight in this direction. Eventually leaves the mapped area. By predicting the guard's route, you can determine which specific positions in the lab will be in the patrol path, including the guard's starting position. The positions visited by the guard are marked with an X. or was it 41 distinct positions in your map? Predict the path of the guard. How many distinct positions will the guard visit? Okay, so this is just like a graph problem. Excuse me. Graph problem, and we have to just simulate the guard moving. Cool. So let's do direction. Well, we'll call this up is. What is this? We want to increase the row. We want to decrease the row, rather. Leave the columns the same. Down is 1, 0. Left is 0. Decrease the column. Right is 0, 1. The guard starts. Where's the guard start? Let's get our input. I'm assuming that the guard is going up. Let's see if that's the case. Yeah, cool. All right. So we're going to have grid is lines. For row in grid, for a call in grid, we're going to find guard pause is none. We're just going to find the position of the guard starting. If grid row column is this, guard pause, oh man, becomes, we're also going to need visited. This is just a list of positions that we've visited. I'm going to have this not be a tuple just so that we can add stuff to it easily. This is going to be row column, and we'll do visited dot append row column. This should actually probably be a tuple. It'll be a list of tuples. Okay, and then we can break. And let's print guard pause just to make sure that we've got the right spot here. No, we're not day 6. CD day 6. Right, because we didn't actually give any input, huh? So we'll do the test input. This should be, what is this? 0, 1, 2, 3, 4. The 4th column and the 6th row. Oh, range length grid. Yep, silly me. Range length grid. 6, 4. Cool. That seems to work. So that's our row column coordinate. Then now we need to do a thing where we actually run the game. So we'll call this run game. We'll take in the grid, guard, pause, direction. Cool. So I think we're going to return, and then we also need the visited, I guess. I think this is I'm trying to decide if I want to do this recursively or not. I guess it doesn't really matter. So we'll go not recursive. So we'll do while guard pause. We'll do guard row is guard pause 0. Guard call is guard pause 1. While 0 is less than guard row is less than length of grid, and 0 is less than guard column is less than length of 0. We want to So I guess the question is when to turn. If the guard is about to hit an obstacle, I guess that's probably the thing to do. If the guard is about to hit an obstacle, turn. So we'll at some point have to deal with the turn logic. But first, the thing I want to do is So, okay, let's simulate moving and then see, get the next position and then see where that will put us. So, next row is guard position 0 plus direction 0. Next column is guard position 1 plus direction 1. So if that takes us off the grid, return. So maybe we want to do this check down here. We could just have this be a while true. And then if not, or not. I don't think we need these parentheses, which doesn't hurt. We can return. Length of visited. Otherwise, if there is no obstacle, continue. So I'm actually going to handle the obstacle case. If there is an obstacle, turn right and try again. So my concern here is, so I guess we'll just turn. We won't increment. We'll do get next direction, and we'll get direction. If direction is up, return right. These have to be top level. Where's my function? Oh, there it is. If direction is right, return down. If direction is down, return left. Then return up. As our default if none of these hit. Okay, so then direction becomes get next direction, direction. Then we can continue. But if grid next row, next column is this, then we want to change direction. I'm wondering if we actually need to do anything here. We're incrementing our. No, I guess we do. Mark visited. Pen. Oh, but we don't know double count. Visited, not in. Or if this. Next row, next column, not in visited. I should probably use a different key or something. This should probably be like a string. Like concatenate like row, comma, column, and put it in visited. But I'm not going to do that because I'm extremely lazy. If there's no obstacle, then we can mark it visited, and we can advance the guard position. Guard position becomes yeah, I'm not using these at all, am I? Guard column. Where's... Oh, this should be guard row. No, this should be next row. Yeah. Next call. And then guard pause will become next row, next call. And then at the end, we'll just return visited. So let's try that. Let's try total visited becomes run game on. What do we need? Grid visited. Guard position. And direction is up to start. And then let's print total visited, and we'll print length of total visited. All right, let's try that. What? Oh, return. I see. Yep, that's dumb. Yeah, we're never actually breaking the loop, so that doesn't seem right to me. Yeah, that doesn't seem right at all. Okay, so 6454 4434 2414. All right, probably what we should do is, you know, we actually don't even have to keep track of. Don't have to keep track of visited necessarily. We can just mark the grid. Let's just print the grid. For row in grid, print row. And then when we mark visited, we will do grid. Next row, next column becomes X. Oh, whatever. Yeah. That's kind of annoying. So we have strings, so we want to do L for L in lines. It's not quite what we want though. This just does the same thing. So we want, let's see, L for N for N in L. Let's see if that does what we want. Okay, that does do what we want. It's kind of gross. Let's do that joint so we can see a little bit better. Okay, so this is actually almost right. We've gone straight up, and then we don't turn right. So let's see what's happening here. Print changing direction to direction. Oh, interesting. So that never happens. We just 0 is less than. I'm just wondering why we're deciding to go off the end here. Next row would be off grid. We'll do row next row, next call. 0 is not. Next column. I mean, so this is definitely an issue, but I don't think that's the only one. Next coordinate will be off grid if. Zero is less than next row. Oh man, Booleans are hard. There we go. All right, so that seems to do what we want. 41. Cool. Let's try with our actual input and see if we get anything sensible. 47.76. Great. Excellent. There's part 1. Okay, while historians begin working around the guard's patrol route, we borrow our other fancy device and step outside the lab. Return seems like a few seconds later, but area's too large. They're pretty sure that adding a single new obstruction won't cut the time paradox. Okay. New obstruction in such a way that guards will get stuck in a loop, making the rest of the lab safe to search. I'd like to know all the possible options for such an obstruction. It can't be placed in the guard's certain position. At least 6 different positions where a new obstruction will cause the guard to get stuck in a loop. The diagram should be 6. Holy moly. Okay. How many different positions can you choose for this obstruction? Wow, okay, so this is asking us to find a loop. Okay. So... Advent of code is hard this year. That's crazy. Okay, so we have to add a new obstacle and then see if that results in a loop. How do we detect a loop without our program crashing? That's the question I have. Because, I mean, we can't... It's not ideal, obviously, but we can just brute force it again. Speaking of brute forcing not being ideal, I'm trying to brute force day 5 part 2, and we found one answer out of like 200, so that's gonna be a while. Thinking. So if we travel the same... We know it's a loop if we travel it multiple times, meaning if we ever close a loop, there's no way to break out of it. That's obvious, but how do we formalize that so that we can code it? Oh, but this is a loop with the... Oh, look at this. Right, that's a loop within a loop. Wondering if it's possible to get... I'm confused. Go up like that. Round. And then like that, I think, is where we hit the loop. Okay, so we need some way of comparing the path that we've taken to any particular point. And if we reach that point with the same... No. So if we reach a point and we've been to that point before. Is there any way we can't be in a loop? Does that make sense? No, I don't think there is. So if we reach a point and we've been to that point with the same orientation before, I don't think there's any way we're not in a loop. So I think all we have to do is add a check for if we've been in a position and we've seen and we've been in that position before with the same orientation. So we just need to add our direction to our visited. So let me just copy this to part 2. Run game 2. Cool. So we want to detect a loop. So instead of returning visited, we want to return is loop. So this would be false. So I guess where do we detect a loop? If next position puts us in a place we've been with the same orientation, we are in a loop. Return true. So now we want to check if we want to check if we're in a loop. That sentence wasn't very coherent. I'm just trying to think how so I think we'll have like visited with loop, or we'll call this visited with direction. We'll have this be a dictionary, so it's fast because we're going to be doing this a lot, I feel like. And we'll have this be our key. Let's have a function that gets a key. Def get key for visited, and we'll have our pause, and we'll have our direction. And we'll return F. That doesn't actually matter. We can do. That's not how that works. We want F. No, that's not at all. I want F position 0. Position 1, and then direction. So if get key for visited for our guard, this is not going to be our next position. It's going to be, sorry, it's not going to be our current position. It's going to be our next position. Next row, next column, and this will be our direction. In visited with direction. Return true. So that's a loop. Then we want to I guess we want to change our direction and then add get keep visited here, right? Do we? Or do you want to do it first? I think we want to do it after, because we're never actually going to visit. Yeah, because we'll never visit one of these, so we want to do it after, I think. And then we'll want to do visited with direction of this key becomes true. Okay, so then let's try run game 2. We don't need these variables anymore. so this should return false. Oh. Length of, okay, right, because we don't want is loop, print is loop. Run game, oops, that's not what I wanted. Run game 2 is loop. Print is loop. Okay, false, excellent, that's what we want. Yeah, that's what we want to hear. Cool, so we're going to, oh boy, for row in range length grid, for call in range length grid. So we'll simulate putting a obstacle if there isn't one already, and it's not the start position. If grid row column, and we have to copy our grid because otherwise we'll be adding it to the grid. I don't want to do that. If grid row column is this, or row is guard pause 0 and column is guard pause 1, we'll just continue. Otherwise, copy grid, put chord, send it. And we can just copy, we can just pass in an empty list here. It doesn't actually matter. The sim grid. And then we'll do if is, we don't even need is the, we can just do if run game. We can do total plus equals 1. Total is 0. And then we can print total at the end. Now the only thing we have to do is get this sim grid. We'll do sim grid is get sim grid for grid and our row call that we want to put the obstacle at. So this will just be a function that copies the grid and puts an obstacle where we tell it to. Grid row column. New grid is. Could I show part 1 code? Yeah, I'll show it as soon as I'm done with part 2. It's similar to part 2. Just curious, yeah, it's still going. Cool. New grid is just going to be L for, yeah, this should actually just work. I think if we just use another list comprehension, this should be the same thing. New grid, row, column becomes that, and we can return new grid. So let's see if this works. And then hopefully, I don't think we're printing out anything in run game 2 anymore. Oh, we totally are. Yeah, we probably don't want to do that because that will just take longer. All right, let's see if that works. This is going to take a while. A long while, perhaps. Let me actually kill this because I don't want it to. One more kill. I want to make sure we're not hanging anywhere because it is possible that we're just going to be in an infinite loop. I expect it to take a while, but I don't want it to infinite loop. So let's check. Oh, that's a weird indent. Running game 4. Row column. All right, so let's see what grid dimensions are here. This is going to be like, well, I guess we'll see in a minute. So it's going to be something by 130. Maybe it's 130 by 130? Yeah, 130 by 130. All right, so this will be a while. You know, we could make this a lot faster, actually, by just putting obstacles in the path that the... that we found in part 1. So let's see if we can implement that while this is running. Having the little flashy thing is distracting for me. So we're returning visited here in part 1, right? Yeah. Yeah, this is gonna take a long time. Yeah, we can call this visited. Oh, sure, fine. Then we can do candidates is run game. So this should all be the positions that we could be in. And then we'll change this to B for C in candidates. We will do row gets C0, column is C1. I think we can just do this exact same thing here. Right? Oops. And then we can return. Oh yeah, that's not supposed to be indented. And then we can print total. Twiddle. Cool. Exit. CD day 6 are we on? Yeah, nope, day 6. Python main.py. Yes, this seems to be faster. Right? That seems plausible. Yeah. But I think this will still be slow, but I think we'll beat this original naive implementation by some margin. It's still going to be a little bit, though. Hopefully this works. You know what? This is stupid. I should have tried it on the sample input and made sure that I got the. Well, we're doing a third thing. Try on the sample input. CD day 6 Python main.py. Oh, big L. Oh, because we copied the wrong thing. 6. Cool. All right, so I'm convinced that works. Now I've just got to wait for this to finish. And then we're going back to day 5. I will be right back. Holy guacamole, we're still going. That's crazy. Where's this? Yeah, okay, we're still going. I don't need that anymore. I don't need this anymore. Maybe that'll make this one slightly faster. Kind of seems like it's slowing down a little bit. Oh, maybe not. Now I'm wondering if there's a faster way to do this. I mean, I'm sure there is. But like a faster, I don't know, reasonably gettable way of doing this. There's always like the lead code hardos that get this in like 30 seconds and put the rest of us to shame. 1586. Cool. Hopefully that's it. Otherwise, let's go. Alright, cool. There's day 6. Let's see how we're doing on our leaderboard. Boom. Well, I'm the first one of people on this leaderboard, so you know what? I'll take it. That gives us time now to focus back on day 5. Wow, what a time. Okay. So I'm wondering. So rough.
Nice.
This is never going to work because we need to pass nums as well somehow too. So we need like. I'm so bad at sorting. I really don't like sorting algorithms, and that's what I need to do here. So we're done with day 6. We're back to day 5, part 2, because my incredibly naive implementation is not working at all. Oh, just kidding. We found 1, 2, 3, 4, 5, 6, 7. 7 out of 200. We're getting there. So eventually this will work. Wait, no, I guess I don't want this. Random shuffle. So one optimization we can make immediately is to get rid of I don't even want to optimize this because it's just so dumb. Part 1 code? Oh yeah, sure. I can just push this to GitHub, I guess. Yeah, so this is the, I really wonder why my chat overlay is not working. I gotta fix that for tomorrow. This is part 1. Run game is this. I actually commented this pretty decently. Yeah, so we're checking if we're about to hit an obstacle. If we are, we turn to the right. So that's what the rule is. So that's happening here. First, we check if we're about to go off the end of the grid, and if we are, we don't do that, and we return visited. Because that's the, if we're going off the grid, we're not going to hit any more obstacles. Yeah, otherwise we just continue. We don't do anything, we just continue. So this is concerning to me, actually. I'm wondering why this isn't offending. Okay, so we don't want to randomly shuffle. We want to. So what's a smart way we could go about getting? Whoops! I'm just trying to use a Mac shortcut on Windows. What's a smart way we could go about getting the right order? $75, 47. Maybe we can just have like a a really naive sorting function where we just swap them. What is that? Selection sort? Yeah. Oh, stop giving me ads. This is terrible. Ugh, I hate sorting algorithms so much. Drawing range -1. Assume the current position holds the minimum element. Iterate the unsorted portion to find the actual minimum. Yeah, but that sort of doesn't work because we need to do stuff with the rest of the elements. If that makes sense. So I guess we could just work backwards. What if we find the element that needs to be the highest? Put that. Sorry, lowest, right? That needs to come before the others. Put that 0th, then continue. Okay, so let's see if we can get that working. F get lowest element, and then we'll pass the rules. We'll pass the elements. And then we'll return. We don't have anything to return yet. So we'll pass. This is rules dict, and this is S. There's nothing like passing things in a different order, huh? S rules dict. Okay. I'm gonna time box myself again to another 17 minutes or so, because I don't want to be doing this all night. I think honestly this one's harder than today's. Okay, so then what do we want to do here? How do we find the lowest element? So I guess check the check the first element. If it has something that has to come before it, then check that one. If etc. If we reach one that doesn't have one that needs to come before it, that counts as our lowest. So let's do while current is elements 0. We'll do while current in rules. So while we have something that needs to come before, let's do current. I think just becomes rules current. And then we can just return current. Is it really this easy? This doesn't really get lowest element. It's not really what we're doing. We're just getting one that doesn't have restrictions. Part 2. So let's comment this out and just get lowest element. S rules dict, and then we'll just return. Just to see if this does belong with this E5. Oops, Python main.py. add sequences. The most elements. Hold on. Oh, we're trying to hash a list. Most element while current in rules. Current rules. Oh, and then we're setting, because there can be many. Oh man, is this BFS or DFS? That's insane. All right. Jeez. All right. You know what? We're not gonna have currents. We're gonna have candidates becomes element 0. While crap. Length of candidates is greater than 0. We will do current is candidates.pop. And then we will do if current not in rules, we can return current. No requirements. Otherwise, we want to do candidates.append rules current. Return none. Should never happen. I imagine this will happen immediately though, because that's just how it'd be. Oh, this should be a list here. Oh, come on. Oh, this should be, yeah, this should be candidates plus equals, not append, because reasons. Yeah. So infinite loop for sure, but how can we not? Oh, it's because we're adding to the end. We're not working through them, so we want like candidates. Man. 0, right? Remove and return I meta index. Yeah. That's still an infinite loop. Checking. Current. Yeah, okay, so we're definitely in a loop somehow. I don't know how that could be the case though. Like, oh, because holy moly, this is so hard. Maybe I do want to just let this run forever. Because we have to like filter for the rules that we care about. So I guess these can have cycles, but because of whatever numbers we have, they maybe don't. Elements, rules. Man. So where's part 1? This is so rough. So we want to do. So I guess we have to filter the candidates that we're adding to the filter x in elements. Does that work? Python, filter list. Yeah, filter lambda x. Oh, okay, so lambda x is the thing that we do first. Okay. Sure, and then we want to do rules current. Okay. This is fine. Everything's fine. Did we return none, though? I feel like we returned none. God damn it. Oh, man. Great mess. So, hold on. This should be... make my life easier. For the meantime, this should be our test input. Checking 97. Wait, oh, I see. Okay, actually, that's sort of the answer that we want. Right? 97, and then... oh my god. Okay. Def build list. And then this is going to be elements rules. So we're going to do for for I in range length elements. This. I'm doing 5. Why is the title is day 6? Yeah, so I did day 6 already. I'm now doing day 5 part 2 because I ran out of time last night to do it. I guess I should change the title. Whatever, I got 6 minutes left, it's fine. Let's do result.append, get lowest element, and then this will be elements from I onward, and then this will be rules, and then we'll return result. So let's see what happens if we just build the list like this. Messed my parentheses up. Okay, so that did not work. Oh, because it's not, we can't, alright, sure, fine. Because we have to remove the, sheesh. We have to remove the element that we used, while length of result is less than the length of elements. Whoops. And then we want elements to become filter elements lambda x not in result, right? Oh my god. Function type is not iterable. What do you mean, though? Oh, right. Wait. Oh, yeah. I got these backwards. Let's... List filter. Excellent. All right. Cool. Super cool. That still doesn't work. Somehow. Why though? Print elements. So we knock out 97. Then next we have 75. Maybe we want to return current. $75, 97. Oh, I'm so confused. I got 3 minutes left. You know what? I might just never do day 5. Part 2. Because I am not having a good time with it. Build list. What's our result? It can't be only 3. That doesn't make sense. Okay. Total length is length elements. We don't want to keep evaluating this. Oh. All right. Well, that seems to work. Cool. Kind of pisses me off that it seemed like it was just that easy the whole time, and I just had to use my brain a little bit. Oh, you hate to see it. All right, so let's see if that actually works for the whole thing. God. Result is this, print result, and then we'll just do this. And then we'll print total at the end. You hate to see it. I can't believe. I thought it was gonna be way harder than that. I didn't even try to do it this way because I thought it wouldn't work at all. Oh, it doesn't. At least it doesn't with my code. So what about this? Okay, so we gotta figure out what we're doing here. What was the bad sequence? The one that we didn't like? 34. This is the one. Oh my goodness. 34, 47, 16, 49. Wow, there's a lot of these. What? 13. Oh, because I'm printing. Oh, I see. Doing the wrong thing. Okay, it's 10 o'clock. I really don't want to call it here, but I have my time limit. Alright, let me try one more debug. Let's print S. 8317 is the one that gives us issues. 17. Alright, so if I can't find the issue on this round of debugging, I'm giving up. 83. Get lowest element. Let's try print. Checking. Print. So we check 76, we check 73. we're checking 73, we're checking 76. Let's just print the length of current. Because I have a feeling that we're just perpetually adding. Oh, candidates are there. Yeah, so that's just getting huge. Yeah, I don't know. All right, day 5 part 2 still has me stumped. I'll go think about it for another day, and then maybe tomorrow, after I solve day 7, we'll come back to it again. A lot closer today, though. You know, in the meantime, maybe I'll just let this continue to run. Around what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 out of 200? That's pretty good. We'll get there someday. All right, anyway, thanks for watching day 6 and part of day 5, part 2 again. I'll see y'all tomorrow, same time-ish.